I am going to introduce Dan Stanzione, our next speaker.
We ran him, but yes, thanks very much, Greg, and thanks everybody and Ian Rockmouth for the invite. Been meaning to get up and talk at GlobusWorld for a couple of years. It's great to finally be here, however briefly. So unfortunately, I have to run and give another talk in a couple hours. But the yeah, so my talk has lots of things in the title because I'm never going to get through it all. So, you know, we'll just stop at random somewhere about 30 minutes in. But I run the Texas Advanced Computing Center, and I wanted to talk a little bit about how Globus fits in with what we're doing. And we're evolving through these things called EPIC and the NSF Leadership Computing Facility, and talk a little bit about how this all fits together. But first, for some context that I think Ian teed up in the last session very well. So one, I run kind of a big computing center over in the university academic space. And data, and you can insert your verb, and there are many, right? Movement, curation, access, integration. I guess none of those are actually verbs, but you can insert your own modifier here. But data something is central to pretty much everything we do. And there's some easy ways to see that. I actually pulled from NetSage, which I'm going to talk about, and I think Jason's going to show again in a talk tomorrow. But this is just data into TACC from around the country and around the world. As Ian mentioned, it comes from all over at this point. We had a slow month in January. I guess I pulled this 123 to 423. I pulled this Sunday afternoon, the last 90 days. And I think we had a slow start to the year, but this is 14 petabytes in that we could tag in NetSage that comes to the center from outside the center. So this doesn't count anything, you know, in between machines. There's a little bit of tagging by field of science. Not all of it is tagged, but yeah, 14 million different flows over that 90 days. And I'll tell you, that's a little below average. We're averaging right around 5 petabytes a month. So this is, you know, 4.5 or so petabytes per month. But, you know, people come and stress over moving a petabyte of data. And I'm like, yeah, it's a typical week. But anyway, but not all from one site. But, you know, we have to be able to deal with all this data. And my one big criticism of NetSage is that it has no idea where Austin is. And thinks it is somewhere in Kansas. But other than that, it produces these really great visualizations. So Jason and Jen are cringing somewhere, but so we're not actually north of Oklahoma. We might be a little south of it, but you can see flows from around the country. You see some coming trans-Pacific, some coming transatlantic. This is the top 100 flows by field of science or something like that that come in. But you know, everything we do is dependent on having these data things. So I'll talk about why in a second, but just in case you haven't heard of TACC, just real briefly, I used to have a big long TACC spiel. I got tired of giving it, so now I have a very short TACC spiel. But we run a lot of the big NSF computing platforms, that's Stampede 2 and Frontera, both of which will get replaced over the next couple of years by this thing called the Leadership Class Computing Facility, but we're one of the big NSF operators. Lone Star is our local machine. It runs fully immersed in oil. So if you want to come see chicken fried computing, come on down anytime. So, but it's fully, actually the earlier ones that were white had a glass case. Those were the chicken fryers. These we call the space torpedoes. But we run a lot of the big systems for the National Science Foundation, a lot more for our users in Texas. We run about 20,000 servers. We have about a couple of million cores, 1,000 GPUs. We put out a few billion core hours per year. We ran order 3 million jobs last year. We have 94,000 user accounts. We just audited that, 8,000 or 9,000 run in any given month. And like I mentioned, about 5 petabytes of data show up every month. Another 15 terabytes seems to get generated on Frontera that moves to the archive every day. Another 10 or 15 terabytes out every day. So that gets back to users. So lots and lots of data. So, and we do this all, for all of our work, we do have a lot of protected data, the high assurance, but nothing classified, right? All unclassified open science. Most of our protected data is in the healthcare, a little bit of ITAR, but primarily protected health or other sort of human identifiable information. But, you know, this past year, we did some James Webb Space Telescope stuff. We did Event Horizon Telescope stuff. We had this one, which I think is a great example of functional infrastructure. But there was this New York Times piece last August, while California was in 20-something years of drought, that said, you know, there's this chance of these new kinds of megastorms where atmospheric rivers will line up and hit California one after the other, which happened in December and just finished like 2 weeks ago. So, And this particular project, so I first saw it in the New York Times. One of my more enterprising staff, a data curator, actually went and dug up the Nature or Science paper that this article was written from, then dug through the references and found all the DOIs, and they all came back to us. So this was a project where I'd never actually met the user because we support 3,500-ish projects in any given year. But they had used our infrastructure and published all these data sets on what turned out to be a fairly prescient observation in the last year. But we do all sorts of these sort of science-related things. So why is all this data stuff central to what we do in a computer center? And I think preaching to the choir here, but starting with the obvious things, none of our users are near the machines, despite what you see in occasional movies where people go in and plug a laptop into the supercomputer. That very seldom actually happens, right? Everything is remote. If there's a laptop plugged in, something is horribly broken, right? So nobody's doing actual work at that point. So it turns out none of their experimental or observational equipment is anywhere close to the machine, as many of the examples we saw in the last talk come from. Some of those data sources are as far away as the nearest Lagrange point, like the James Webb, 1 million miles from here. And everything we do, and I like to say we have sort of 3 lines of business in the large scale computing world, right? We have the simulation workflows, where you're going to produce a lot of data, and that's mostly data out. Increasingly, it's data in, because all these simulations are now real time with data assimilation, and you're doing inverse problems to bring in the data points and solve them, which ramps up your compute by a factor of 100 or 1,000, but also means you have to do real-time data assimilation from weather sensors or ocean buoys or any of dozens of instruments, plasma flows and fusion reactors. But we have our simulation-based business where we build sort of PDE-based models of the world and query those models via simulation. We have all these experiments, and Ian mentioned a lot of these workflows, the Advanced Photon Source, et cetera, beamlines, where we need to get at the data and analyze it. That's sort of the analytics stool of what we do. And increasingly lately, it's all AI all the time, everywhere. But that's, lots of data for training. So we're either producing data with simulation, grabbing experimental data for analytics, or taking a whole bunch of training and inference data for AI. And all of those put data at the center. There are many sort of slightly less obvious reasons that data is more and more the focus of what we do. And we talk more about data than computing. One is that there's the general sort of sociological push where publishing data sets or software or containers is becoming as important as papers and manuscripts were. And having those artifacts exist and being referenceable is important. The other one is sensors are cheap, right? The cost of producing a bit of data in the physical world, it's an odd thing to say about digital data in the physical world, but the cost of these sensors, price per bit, falls dramatically, right? If you're doing traffic, there was a time where you'd have the little counters, you still see them on a lot of roads, right? You'd count tires moving over, and you'd have a fairly low bandwidth signal. Now you just grab the 20,000 street cameras that are in Chicago, measuring traffic flow at every intersection, AI identify all the cars and pedestrians, and put these huge data flows together, right? That same thing applies if you're doing wildlife research and trying to find, I have a group who's doing panther tracking in Florida for the few Florida panthers that are left, and identifying which ones have feline, it's not quite leukemia, but the similar sounding disease, by camera traps that only activate when something moves, only take data if the thing that moves happens to look like a panther, and then before it even sends it back, can look at the gait via AI and figure out if that panther is sick or not by how it's moving. So, huge amounts of data reduction at various points in the compute line coming back. So, so price per bit, we can generate ridiculous amounts of data. And as all those examples Ian showed, we have ML and AI in every workflow. The simulations that used to be, let's run this code, have now become ensembles. If you're doing forecasting, you're probably incorporating observations. These workflows are getting bigger and complicated. And then even less sort of obviously is there's a huge government push to have all data simultaneously available openly, but never seen by anyone in China, which involves a fundamental misunderstanding of how the internet works. But there's this sort of combination of psychology, sociology, and government that means we're going to have not a place to go look for data, but a fractured federation of hundreds of official data archives, right? You can go to, data.gov, and you can only find, there's 16,000 data sources registered right now. So we're not going to have one place to get data. We're going to have a bunch and have to go around it. So as a center, we make big investments around data and constant new investments, and in a lot of different ways, right? Obviously, we invest in storage, is a huge piece of what we do. So the strategy has gotten to be, technically there's more tiers than this, but conceptually it's cleaner if we think of this as 4 tiers, right? We have the scratch storage tier that pretty much everybody who's run a cluster knows about, but right, active, it's your active for all the clients to hit, right? Which for us means you can run 500,000 MPI tasks against it. You know, it can talk to 8 to 15,000 clients simultaneously without falling over. It's got to be performant. It's huge. So, you know, tens of petabytes. So we never worry about things like backing that data up. You don't snapshot at that scale. You just want to get performance, right? So we're optimizing performance. So, you know, petabytes per project at terabytes per second, right? Then we move sort of out and we sort of swap persistence and increase integrity and lower performance as you move down the hierarchy, right? But we have our work file system, which is our sort of center-wide storage. Again, a lot of people have a mirror of this, multi-system, longer term, still not really archival at this point, right? There's not a whole lot of data management features, but maybe it's where you park your petabyte of copy of the Cancer Genome Atlas because you're computing against it fairly frequently, or all your AI training sets live there for a year or two while you need them. And then we move out to one of 2 tiers. One is the more traditional archive, still largely tape. We're heading to an exabyte in that, low cost, low power, high integrity are what we're going for there, right? Don't lose archive data. And then we have a publication tier, the on the web, hot media, we're sharing it with the world. This is where APIs like Globus are huge, right? But designed for sharing publicly or in these restricted ways because everything has to be immediately available, completely open and not accessed by anybody who shouldn't see it. So all at the same time. So, and again, in practice, there's home directories and various caching, and we have petabytes of disk in front of the tape, but nonetheless, conceptually, this is sort of how we think about our storage investments. We also have to invest in networks, right? Still going, right? We have lots of data moving in and out clear every day. We have a lot moving between tiers, right? Even among in the center, right? And again, many terabytes per day that just move around internally. We invest in FAIR and all the related concepts, and Rachna talked about this in future directions, right? Around using DataCite, which we use, and some of the other things, but we invest in curation and schemas. Traditionally, that's meant people to curate data. Increasingly, we're pushing into AI metadata extraction. So hopefully it will be less people intensive, but also the curation systems, Fedora, Dataverse, you know, the data management systems around that, and in DOIs and, you know, having services for those. I mentioned we use DataCite for that, which we build into sort of our site-specific portals. So I didn't realize sort of screen size coming in, so this is probably a little small, but the individual text doesn't matter so much. But this is our design safe portal. It's our data repository and working space around natural hazards engineering. And so this is data publications, and you see there was one February 28th and February 21st and February 14th and January 31st, and, you know, bunch this year. We have hundreds of publications here, and publications here aren't papers. It's usually data sets, or it can be papers and manuscripts or PowerPoint slides, but mostly it's things around experiments. And actually for this set, I've selected on the top, we have different kinds of data because there is some curation here. The experimental facilities, there's 6 funded experimental facilities in the NSF, Natural Hazards Engineering Research Infrastructure piece, shake tables and structural labs and wind tunnels and things like that, where you might try and knock a building over with an earthquake or a hurricane, or rip the roof off one more commonly. So, and these are people who ran projects on those facilities and whose both raw data and process data is uploaded. And we collect a whole bunch of metrics on this data. And by the way, this is one of the portals built on that TAPIS platform that Rachna talked about, where Globus is integrated for the data movement pieces already, but maybe in other ways in the future. So when you drill down into one, and I just picked one from a couple of years ago, so there'd be some reuse metrics. This is centrifuge testing of liquefaction-induced down drag on axially loaded piles. And in 8 years of this project, I have successfully learned to say liquefaction, but took a while. But for the California Department of Transportation, and I will tell you, when we get into the sort of, particularly when reviewers show up who want to talk about this as a data repository, they're obsessed with metrics, right? So we've started tracking reuse of these data sets, right? How is having this data be open? What is the impact? And that's hard to do, but there's a lot of projects around that. But this, if you pull up, you go, there's a section for view project metrics right under the summary there, which I'll pull up in a second. But then this is the first of many experiments that make up a project, and there's a DOI there, and you can see citation data. Download this citation in BibTeX or DataCite XML or however you like, and you can see how many downloads and views. And I can't click on it because it's a screenshot, but if I go to the next slide, I have the project metrics here, right, that shows that, hey, this thing was put out and a couple of years ago, starting in June 2021, which is when I think this one was published. It's been hit 600 times by various people. There's usage by quarter. We can drill down into IP address, where they're from for data metrics. But we're now keeping all these metrics using a standard called the Make Your Data Count project, and all of their statistics get published there. There's a link to go to the standard on how to collect these so we can compare it across repositories and building in those. So huge amount of investment there, but most of our investment in data goes to software and services, right? There's moving stuff around, which is the traditional Globus core from the good old days. And then there's all this other stuff that we've been working on too, sometimes with Globus, sometimes sort of growing it independently, but publication management, APIs, serverless compute, like the FunkX stuff that Kyle does. Kyle's here somewhere. I think he's in the back. Hi, Kyle. Our version with Joe Stubbs, who Rachna mentioned, is Tapas Abaco. Those mostly both exist because we both started on them like 10 years ago. But increasingly, we're doing integration for streaming data. So it's not just file or object data, but having active streams from instruments. Increasingly taking AI support and building intelligence into this infrastructure. I mentioned automated metadata extraction, but also automated other things. We can take, like, for one of the experimental facilities, we can go across all the projects and say, show me every building where the axial stress was above 40 kilopascals. And it'll just, we don't have schemas that define that for the data, but it'll mine the data in its 9 bazillion different formats and pull out all the projects that have relevant data to that query via AI. So, and then we invest in the people and tools to get from the end user to production science. And many of you know, and it is, by the way, nice to see so many familiar faces here, but that Jennifer Schopf moved down from IU to TACC last year. And so the EPIC Center is now part of TACC, the Engagement and Performance Operations Center. Jason's going to talk about one aspect of this. Jason Zarowski from ESNet is here and is going to speak later, but he's going to talk about one piece of this. But just in general, it's part of, well, this is the people side of making sure we can get to remote endpoints to make people talk. So, we have networks, we know the data is remote, we try and build friendly tools for them, but people still need some help periodically with that. So it's funded by NSF CC Star, and the focus is always, I really like this theme, the smallest difference for the biggest change, right? Which is usually stop doing one stupid thing and everything gets better, right? So, and it's partnerships up and down, but sort of a focus on the smaller places. So the idea is understand the use cases on a given campus. I mentioned the theme. There's support for regional, national, international, but debugging mostly network complications through the ability to monitor things, right? I mean, questions have already popped up today, but what about the firewall? But what about this? But what about that, right? And how many times have any of us moving data from site to site found the place where somebody just moved one wire, it got 400 times quicker, right? So because it was into the wrong or misconfigured port somewhere, usually at a medical school, not to call those people out, but every instance I can remember of it has been at a medical school, and I can remember very many. But there was one fairly infamous incident that resulted in some jobs changing for various people, where I got on with the CIO of large cancer centers in Texas who you can identify. And finally I said, look, I hope you're not paying more than 40 bucks a month for your network, because my home network in my living room gets 35 times the bandwidth to TACC that you guys do. And all the places we can, and we're moving 5 terabytes an hour from Stillwater, Oklahoma through the switch in the same building where your fiber runs in Houston, for the large cancer center that will remain nameless, but is in Houston. So the and they get 700 times the bandwidth you do, and yes, the next day it was 700 times faster, and people had new jobs. So because it turns out they were paying more than 40 bucks a month. And they should outrun my cable modem. But anyway, data mobility's part. Can we move data quickly? That's what Jason's going to talk about. But ideally, most of these sort of engagements are with people who don't have an R1 or a large NSF center, although the last one was with NIST. which is in the agency world sort of lost and not in R1. But anyway, so there's sort of 5 big focus areas, what they call roadside assistance, the application deep dives, data mobility. Jason will talk about the network analysis, NetSage, where I drew those plots that don't know where Austin is, and then a training component. Roadside assistance is something broke and you need help right now, right? So, and they basically run a help desk for this. And by the way, each of them has a cool little logo with some auto-related theme, and you can pick up stickers. It's supercomputing related to each of these things. But the epic roadside assistance is, last week I could move files, famous last words, right? This worked last week. I'm doing the same thing. You're not doing the same thing, but they say they're doing the same thing and it now doesn't work. We actually added checksums that run on every job script and binary that people run through. So when they say they're running the same job last week, we can say yes, except you recompiled the code with a different version and took different data files. But other than that, it's the same. But yes, what broke, right? So flat tire crash repair is the analogy, right? You get a response within 24 hours. Somebody is assigned to help you follow up the issues. And it's sort of a researcher assistance site. And usually this is not, this thing worked on my laptop and now it doesn't work on the laptop. It was, I was transferring stuff to Argonne or to TACC or to some center where I'm working remotely, and now I can't get to those resources anymore. What's happened? You know, people to help with that, right? This is mostly about people making the technology to work, right? There's 80 or 90 of those a year. 10% of them typically involve Globus one way or another. People looking, often, I have slow data transfers, how do I make them better? This is the starting point for a lot. Some come from the Globus team, are referred to the Epic team for help. Some go the other way, right? So Jason, again, will show in his data mobility thing, where it's like, hey, you're bad at this, use Globus, and then you will be less bad at it. But general, just debugging end-to-end support to improve performance between sites. The deep dive, if the roadside assistance is what you do after a flat tire, this is your regular maintenance, right? So where you go in, so we have the tune-up thing here. It's based on what ESNet, the DOE network, does in the facility requirements reviews. It's a way to get cheap consultants on campus. If you work in an IT shop and you've noticed whenever your boss wants to make a change, they hire an expensive consultant to say the things they want to say, and then they make said change. If you ever wanted to have your own consultants come in and tell your boss that, gee, you know, this would work much better if you didn't have this one person in research computing doing 23 people's jobs, and you need an external person to say that to them, this might be a great way to get that done, because of that last bullet, which says often the issues identified have nothing to do with networks and everything to do with sociology. So, and again, there's some details here. I'm looking at my watch and going to go faster, but of how that happens. But the idea is write a report. Again, the last one just finished up with NIST. As to sort of what is your CI needs and how can you get there. So, and then the software piece is NetSage, where we look at traffic, understanding your traffic patterns, your currents in and out. This was something that Indiana started with Lawrence Berkeley and the ESNet folks and the University of Hawaii, where it's now the developers have moved down to TACC, with although some work is still done at IU on this. There's 2,500 endpoints in 85 countries to measure things like who's using my network and why is it slow or why is it fast or what's going on. So there is ongoing work planned to integrate NetSage more deeply with Globus Connect. So we can pull Globus Connect log data and look at Globus flows versus non-Globus flows and actually identify the difference for people and show the advantage of that. All of those will be implemented at the NSF access sites, the various universities operating resources through access sometime in the next 6 months. So we hopefully will have more good Globus examples, but you want to look for things like this, right? Why does it slow only run at 4 megabits per second over my 100 gigabit network, right? What does this pattern of bursts happen? I know at TACC, we said it's sort of a 20 gigabit floor with 80 gigabit bursts on a given day of data moving in over the 100 gig feeds. So why is that? In this particular one, when you identified the route, why does this data go from Singapore to Taiwan via Los Angeles? Seems like a suboptimal path. So NetSage is about answering all those kinds of questions. And again, data mobility, Jason will talk about, which is, can you move a terabyte of data in an hour or not from your site to another site? And he'll talk about that. Here's typical flows from in-car, for instance, where we move 8,000 flows with 7 terabytes over a period of time. So last thing I want to talk about with my last 2 or 3 minutes here is I've talked about a lot of the strategies we're using. We are upgrading the facility to do all of this, right? And so the thing that's coming down the pipe is the leadership class computing facility. And we're still not completely, we've been funded for planning. We've made it through the various design phases to final design, but we are awaiting Congress passing the next fiscal year's budget for the actual start of construction. So that's going to be sometime between October and 2030 is my current forecast on that. But hypothetically, we start March 1st of 24, so about 11 months, 10 months from now. But you'll see a lot of the things I mentioned in data strategy implemented here. This is a big investment. It's a long-term investment by NSF in computing of the kind they haven't made in the last couple of decades, probably since Blue Waters was the last time they really spent money. And longer than that for sort of holistic spending and computing, networking, software, people. So the construction budget's around $400 million. So it is significant. Part of that is facilities to actually host machines. So we're building a custom built. We're not going to own the building this time. We're going to have a colo facility or colo company build the facility to our spec. So it'll handle the things that colo facilities don't do, like direct liquid cooling and 100 kilowatt plus racks and high density networks and all those sorts of things. Yes, there'll be a computer. Yes, it will have accelerators. In proud TACC tradition, yes, it will also have a lot of CPU based. I can't give you all the architecture details at this point, mainly because the chips aren't finished, but so core counts and yields and clock rates to be determined. But we will have more than 1 million cores of CPU in the next machine, along with an awful lot of accelerators. So it'll be, for those of you who've used Frontera, 10x Frontera in peak performance and HPL performance at about 1.5 the power, about 12x for the applications we're looking at. But for AI, it's about 100x where we were on Frontera with about 10x ops. Yes, it will have more memory and network, 3 petabytes plus of RAM, 1.75 petabits per second bisection bandwidth. So the internal network, and that is petabits, will be pretty fast. But then we'll have dark fiber back to TACC, and then 800, we'll start with 2 400 gigs into it, and then move to 2 terabit links from outside. There'll be additional systems and personnel scattered around the country. Not surprisingly at Urbana-Champaign, San Diego, Pittsburgh, and Atlanta. But all of those 4 tiers of storage I mentioned earlier will be represented in this new investment, including the publications tier, the archive tier, and the HPC-oriented tiers. We're going to get rid of spinning disk largely in this. So we'll have 400 plus petabytes in those first 3 tiers, all in QLC flash technology of some form or another. So because the archive, of course, will still be tape, but we'll have about an exabyte of that. But you can expect sort of 10 terabytes a second of IO bandwidth with that level of flash. So for most people, they're going to see sort of 25x improvement in IO, and even better if you're doing small file, high IOPS, also known as AI, and maybe no luster. So luster is the pain point for everyone. Maybe it goes away at long last. So, and we will have support for all the software services that we've never had in our very constrained budgets for normal HPC. So, APIs supported first class Kubernetes partitions. So if your FunkX workflows need a container to run out of, there'll be a Kubernetes partition in the machine to go do that stuff right away. Tapas, portals and Jupyter support, lots of investment in software stack and people. And of course, we'll have Globus. So I'm now officially out of time because Greg's standing over there. And again, lots of investment in services because that's key. Hopefully with continued partnership with Globus in moving, monitoring, and managing all of our data moving forward. And with that, thank you very much to all my team that makes this happen. And I'll stop there.
Thanks, Dan. I will give you a quick question if somebody's got a quick question, because I took some of your time at the beginning. So do we have any questions for Dan? No? Okay. I actually have a quick comment. Okay. I'm going to tie this back to GlobusWorld 2 years ago. There was a joint project between TACC, Globus, and Jason's team at ESNet where we moved the data from the Arecibo telescope. So that was a whole lot of data that you now have in-house.
Yeah, you say it like it's done. So the Arecibo one is an interesting story, right? All the online data moved as part of that project 2 years ago. And they had data on disk, and, again, thinking about all the places you have to make investment are important, and Arecibo had no real network connection. So all that disk had to get driven to San Juan to get moved, and there was 3 or 4 petabytes dating back to 1964. And all the online data is moved and safely ensconced in Ranch, the archive system at TACC. Then there are rooms full of tapes that they claim are been stored in climate-controlled environments in an island that lost power for 6 months after the last hurricane. So I'm sure they haven't been stored in high humidity jungle conditions for the last 40, 50 years. They're made by fine tape manufacturers currently in business like Compaq and Maxell, 8mm DAT tapes, and just getting them out of there seems to be beyond there. So Jason, who is here somewhere, is there he is, right here in the front. Sorry, I'm staring into the spotlight. Yeah, you're just black spots to me. Is leading our commando raid into the jungle in next month, I believe, with Nathaniel Mendoza and some others to go liberate the tapes of Arecibo in a data liberation mission that we're funding soon. So, yeah, so there's some of these things have really interesting backstories. We can get into them.
Okay, great. Thank you, Dan.
All right, thanks everybody.
Okay, thanks. Okay, our next group, I shouldn't say old friends, I should say longtime friends of Globus. How about that? One of the cool things about Harvard and what is what they're doing, right? It's a story about connecting the whole research computing cluster with in the research computing department with the where Scott works, with the enterprise IT department where Helen works. So yeah, I'll introduce Scott Yokel. He's the University Research Computing Officer at Harvard, and Helen Ziwa, the Director of Strategy and Engineering at Harvard University. So take it away.
Greg, we need the mic.
Somebody else.
Hello, good afternoon. So we'll try to speed it up. Scott and I are here to present on how Harvard is planning to go beyond Globus Connect. And so the question we like to ask researchers when we talk to them are a couple, and we'd like you to keep them in mind as we're talking. What challenges do you face in sharing and publishing research data? And what technology and tooling would you like to see in place to reduce the friction in your research process? And, you know, we're by no means coming here as experts. We are sharing some things that we've tried, looking for feedback, looking for questions and suggestions. And what we'll just a very quick outline is we'll give you some stats about how we're using Globus at Harvard, explain some use cases that we have, and then an overview of the Harvard Data Commons project, explain the ecosystem of tools that we envision, some example related to the NESI tape, and an MVP example, and then wrap it up with what we are doing about the Google Drive conundrum. And Scott will kick us off, and then I'll come back in.
Is this one on too? Can you hear me with this? Okay, good.
Go for it.
Yeah. All right, thanks. Just to give a brief overview. Whoa, is that better?
Yeah, there's a switch on.
Did you get yours? All right. Just a brief overview at Harvard. There is that still echoing out there? All right. The campus is pretty broad in a sense. It's not all in one location. So what I'm demonstrating here is that there's also numerous groups of research computing. There's groups that are using Globus that are also in the libraries and in central central IT as well, as Helen was talking about. Anyway, so we end up having like 14 separate managed endpoints across the campus. The campus also exists network-wise in downtown Boston as a part of a colo facility where our network hub is at. It also exists in Holyoke, Mass, which is 120 miles west in central Mass, where the Massachusetts Green High Performance Computing Center is. So this is just a snapshot of kind of the top 5 endpoints. So one of the things that's interesting, I was just going to point out, is that this unique users that is listed there, and also thanks for Greg working me like, I need stats, I need more stats in the last couple of weeks. is that so the unique users, what that really is telling you is how many projects are using it, right? Because an initial like lab manager or PI will go in and create a GlobusShare, and then they will then share out and create guest collections, right? So that's something just to point out. And it's the other thing that's really funny is that the Northeast Storage Exchange, which I'll talk more about later, the only reason why you see two unique users is because those are system users. All of the rest of it is through collections in that space. But there's a significant amount of data transfer that's happening. You can see millions of files in a year that are happening through some of the major endpoints. You can see whether it be terabytes from individual endpoints or petabytes from endpoints that are being transferred. So that's just something to point out. So it's being heavily used. This is the typical I'm transferring data space. So that's the managed endpoints. The User Plus, I talked about User Plus as a talk a number of years ago when I was here at GlobusWorld. One of the examples of that is where like they want to deploy a Globus endpoint, but they do not want to deploy a managed endpoint. So one example we have is actually a famous course called CS50. There's kind of a rock star of a faculty. If you actually have high schoolers that go to, I think it's code.org to like take a class, it's actually they're taking a Harvard CS50 class is one of them. And so they film all this course and they make this virtual interactive space. So there's all this video editing. So they have this suite of like high performance workstations where they're deploying Globus endpoints, and then they push and pull them back to the data center, just not to do work, but just to have a large scale storage, right? So we as the HPC storage providers end up being like a cloud provider for storage to this group. So that's an example. There's lots and lots of examples for instruments, the HPC data storage. Unfortunately, we don't leverage all the cool new techniques yet because a lot of times researchers are responsible for that. We don't have the bandwidth for our staff yet to go in to do all this work. But I feel like I should push them to do that now that I know how much new things happen. But this is just an example of one of the largest data producers on campus. This is a Siemens multi-headed scanning electron microscope. There's 61 scanning electron microscopes inside of that box. So every 2 seconds, it takes 61 TIFF images that are anywhere between 100 to 500 megabytes a piece. It can create 2 to 3 terabytes an hour, right? So Zeiss has, that's 61. There's a 91 and like a 313 number of heads instruments that exist out there. And so those are all creating a huge amount of data, and that's the flow. And like we said before, the problem is locally in that lab, they have to do quality control. Like the instrument operator wants to ensure that all of the brain tissue that they're about to scan is actually working correctly before they go through the process to destroy all of it in the process of making the images. So there's a lot of QA/QC that happens in the lab before data transfer happens. Other examples, I'll talk in detail later about the Northeast Storage Exchange. I will talk about Harvard Dataverse. I will talk about, or I should say Helen will talk about Google Drive. And then I'm not going to talk about, but one of the things we just implemented this week was in our new regulated data environment, we are leveraging our new subscription, and we connected to the S3 connector in AWS. And that's the way we'll move data in and out of the regulated data space. It will get analysis run on it and then actually go into the FSMA environment. So my colleague, Imre, just joined the university. He's the university research and data officer. I'm the computing officer. So I worry about computing and infrastructure and all that. He worries about data management, data compliance, those types of things. So he has a lot of interface with the library. And I worry about the infrastructure to support a lot of these tools. So data commons is what we'll talk about for a second. This is kind of his part of the presentation. He wasn't able to be here. Data is created in all sorts of places. And we have a lot of different styles. Like at Harvard or any comprehensive research institution, you have a lot of different types and uses of data, right? It's not all scientific, you know? And so there is a huge problem that we present. Like, I feel like we still present a very similar tool set to researchers as we have for a decade, right? Although their number of files and the size of their files are multiple orders of magnitude more than those tools. And so the other aspect is, even if we can provide them new tools in each of these categories, like planning, storage, analysis, management, and disposal, they're having to manually do each of these steps, and they hate it because you have people who come into your universities who've now grown up with things like Google Tool Suite as being taught in elementary school all the way up. They feel like all the tools in their research life should operate in like those tools do. And so we really need to make these things easier, make it easy for them to do reproducibility, make it easier for them to share data, make it easier for them to understand the provenance of the data, especially as things like software updates to a microscope can change the quality of their data and change the aspects. So like, there's a lot of metadata that we should be collecting and helping them with along the way that they shouldn't have to input. And then we also need to provide metrics on the use. How do we think about data as an asset? Well, we can't do that if we have no metrics on the data, the access and all that. And I think you saw a lot of that information that in the last two talks. So simply the data commons vision is to improve that research experience through automating these workflows. I'm not going to read all of this off to you. This is a typical slide you have to present to get funding at Harvard. But I will say that the near-term objectives are things that we're trying to accomplish in the next year. So we've done some work, which we'll see in a second, but the next phase of it is really to do a discovery phase and go out to the researchers and canvas what is working well for them now in the set of tools, what are the gaps. We want to be able to really hone in on what our next efforts will be. You know, how will we leverage Globus and the new things they're doing? How will we design that to engage with other platforms that we are choosing? And the other thing I'll point out from this is that this is not a research computing focused, I'll call it ecosystem. It's not a project, it's not a program, it's much more than that. It's engaging with library, with university research computing, within central administration, with the school-based services, and the Office of VP of Research. It's really important to have that cohesion. And it's also really important to write down what your plans are, because we had the turnover of the CIO and the VP of Research, and we also had a brand new university librarian. But we were able to carry forward with a number of these programs because of the way the structures of these silly slides that you have to fill out. But it was really transformative. And so here's kind of our first attempt to give you kind of a better picture of what we're talking about. So one of the things I want to point out is that we have these different types of researchers. I just kind of randomly chose different folks like scientists versus digital humanities, data scientists, you even have educators. And so their needs are widely different. And they also use these services at different capacities too. So the one thing I will point out is that we do want some type of portal, right, that they can come to find the things, not necessarily be the portal that does all the things. And it's important for you to understand that behind each of these major categories, like planning, there are a group of like data service specialists, right? They don't exist in one place, but the researchers think they should. So those people who are in the library versus data management, that might be in research computing, all of that needs to exist as an ecosystem that is seamless. And so that's what we're trying to accomplish, right? We're trying to change culture on the back end of how we present ourselves to researchers. We can easily choose tools. We have a data management tool. We have DUA and IRB databases that collect all this information. We have electronic lab notebooks, but none of these things talk to each other, right? A user who goes into a data use agreement or IRB and fills out a list that is approved to work on that data does not translate currently into their access when the data goes to a research computing environment, and thus it should. So that's some of the kind of things that we're trying to work on the back end, work on the movement of data between systems. So that's just a summary of that. A few things on the current state. So these are examples of things that are in production, right? So instead of what I just talked about with things that are kind of visionary and upcoming, these are things that are in production. So the Northeast Storage Exchange was an NSF-funded project within the Massachusetts Green High Performance Computing Center. I was a co-PI. My group within Harvard was the operators of this. We essentially have deployed Ceph and TACC. Those are the two storage offerings. The storage offerings are offerings to other data managers within MJPC, so other research computing groups. They're not to end users. That's not the direct user of the NESI storage. So the reason why Globus was really interested in this space is that we needed a way to provide access to data to end users, but without having to have any connection to identity management. So essentially, the only accounts that exist are just a system account, right? And then we're able to provide a owner of media, so a person comes in and buys physical servers or buys tape media and is managed by the NESI engineers, we can then turn around and provide them access as a managed endpoint or a mapped collection, and then they can create their guest collections that they can share out to. And so we're also offloading management from the Northeast Storage Exchange back to the research computing groups. So there's a beauty in that, because I don't know of any other access mechanisms to do that. If this was an S3 bucket, I could only just give access to the bucket, right? Read and write access. So the individual access to be able to allow users to revoke access. So a lab manager or a PI can revoke access. They can add whoever they want, manage their own groups. It's really a nice benefit. And we leverage on the Spectrum Archive, Spectrum Scale side, some code base that works with Globus, so that when you retrieve data, it doesn't just fail because it doesn't exist on the data transfer node because it only exists on tape. It actually puts a weight into the command. If you use something else like min.io, it just fails the first time, and you do it the second time, then the data has been refreshed, and then you can actually transfer data. So I'm just pointing that out too. A couple other things that we have done a little bit of work in the data commons space. These are the 3 objectives. So I also remind you that these are things that overlap with heavily with Harvard Data Commons, which is also part of what you heard earlier, the NIH, it's called GRAY, the acronym for the Generalist Repository. So some of this work we started prior to receiving that award, and then we were doing follow-on work in that space. So in Dataverse, Harvard Dataverse has multiple millions of files as a repository. You can, it has, I think, 200,000 or 300,000 data sets. In the process, what happens is the normal process is you push data into Dataverse. It actually goes through the portal. It's uploaded via normally like some HTTP call. It injects and does an inspection of all the data, creates metadata about it. It all goes into a database, and then the data is stored all within Dataverse. That process in the past has not led to large data sets because of the way in which Dataverse was created for social science data, and it was architected like 10 years ago. So these improvements on number 1 are to improve that. Number 2 is enhance Dataverse to also allow, so instead of just having data, you also want to have information about how you created that data in some kind of workflow or container. So it treats those in the same way that it treats information about data, as far as the metadata and being able to search for them. And the other aspect is that at Harvard, we also have an open repository for the journals, which is called Dash. We also have a formal archiving service, which is called DRS, the Digital Repository Service. So there are so then you also have Dataverse, which is more of a research product. So you have multiple modes of where things go, but there's no metadata about any of these things, and they're not connected. So to connect all of those, the backend, the data sources of those was the other part of the project. So I'm only going to dive into the first one because I think it's related to what we're doing here at in Globus. And so I just wanted to point out that a few of these things are available in the new versions of Globus, and I think the most interesting ones are the Dataverse, and the Globus phase will be coming out, and then the remote store is also another part. So the pictures on the next page probably help out a little bit. I'm glad they're much larger there because they're tiny on my screen. First, point your attention to the top right. So originally, when you upload just directly through Dataverse, you're limited to gigabyte size files uploads. You cannot upload really large files the way it's designed. So the idea, if you look to on the left, the other thing that we added is that we were only uploading via POSIX, right, on the front end. So there was an implementation to upload and allow S3 on the back end, which allows slightly larger uploads of data. The next thing that was done was this Globus transfer to Dataverse. So in that small box, what happens is when you click Globus as an option to transfer your data in on your data ingest web screen, it then opens up this Globus transfer tool in front of your screen. So then at that point, you're using your normal, like, I want to select these files and I want to transfer. So what's great is you can transfer them like from another endpoint, which would be like different research computing endpoint, through into Globus. with that transfer mechanism. And it also allows the reverse. Like there's something that seems somewhat large in Globus, or sorry, in Dataverse I want to transfer via Globus. You can select how you want to do the download. And that is a collaboration that the Canadian group Scholars Portal is doing, and there's been more work done at Harvard in collaboration with them. And so to combine that concept with the remote storage agent is where I think the power of the change that's happened. So the remote storage agent simply allows you not to have to actually deposit the data into Dataverse, which if you have a really large collection, but you want all the metadata, you want to get a DOI for it, and you want to be able to make it, searchable and findable and all the things to make it fair, but you still want access to that data and not have to duplicate it because you're still doing research on it. That's where the remote storage agent comes in. So it does the ingestion process and creates all the metadata and all the links to the files within the database, but it points back to your local research computing data source. So, and it can also do that now with Globus, which is really handy. So that's really important because on the previous slide, I talked about Nessie tape. So now we have a mechanism to have Globus on the front end as an ingest point, and the data can either be ingested through Globus to Nessie tape, or if you already own Nessie tape, or if you have tape you have somewhere else on some other endpoint, you can index it through Globus and have these really massive, multi-petabyte data sets that can be findable. And you can have a lot of the metadata from the individual files. So that's the end of me talking. I'll now turn it over to Helen.
All right. How do you solve a problem like Google? So one of the biggest use cases that we have found, so for Google Drive, we've done a lot of commiserating and talking about how unfair it is, how much time it's taking, and now we're transitioning to actually doing something about it. So we found in our environment that about 0.4 of the users were using 80%, over 80% of the Google Drive storage, and many of them using it for cold storage. So one of the things that we want to do is enable them to have cloud archival storage and using Globus to facilitate that. So we're in the process of implementing this. The technological solution, the picture looks very simplistic, but we've been discussing the implications of, okay, what does it mean to allow or let researchers store things in the cloud? How are they paying for it? How are you ensuring that you're enabling that process and other things that we need to figure out at a campus level? So more to come on that. We haven't figured it out, but we're having the conversations. But that's policy side, and we don't want the technology side to be the thing that prevents this. So this is what we've invested in premium cloud connectors. We are going to use dump into S3 and use lifecycle rules to move it to Glacier. And then we need to think about, okay, then how do they do the reverse thing? And then earlier today, someone had asked, have you seen Google Drive to Google Cloud Archives? We haven't seen it yet, but we're gonna try to do it because Google has said it works, and so we'll figure it out. We'll let you know what we find. And so this picture, so initially we will have our engineers manually provisioning the storage targets, but we've been talking, Rachna and I have been talking about this idea of using Globus flows to automate the creation of S3 buckets. And we think that if we could automate it, then we could potentially automate the creation of storage targets on any other S3-like storage. And how this would work is, we talked about I mentioned the idea of collecting, how are people going to pay for it, right? You're a researcher, you want S3 storage, okay, good. You come and you decide, this is what I want. we collect from you how you're going to pay, right? Before we move on. And then there's an approval stage, right? We create an S3 bucket via a mapped collection and create a guest collection on that S3 bucket, and then set the user as the access manager for this, so they can share with people as they need. There's notifications that need to go out. So there are pieces here that are already built. So there's send action notification action provider is already built. And then Globus would help us build the new action provider, which would actually be creating the buckets and setting the user access. And one of the questions I wanted to ask is, would this kind of thing be interesting to any of you? And I'll finish by sharing the questions that we started with for you to think about, and we'll take questions.
Speaker is from Argonne National Laboratory at the Advanced Photon Source. And with the relationship between the Chicago and Argonne National Laboratory, it's kind of a test bed for a lot of things that we do, especially, you know, when we started to think about flows and instrument use cases. And there's no better instrument, no bigger instrument than the Advanced Photon Source at Argonne National Laboratory. So Hannah Paraga is a software engineer at the APS, and she's going to be talking about how they leveraged Globus services at the APS. Take it away, Hannah.
Great, thank you all for having me. So today I would like to share with you how we are creating these solutions for big data at the Advanced Photon Source, and how we are leveraging the services provided by Globus. So the Advanced Photon Source is one of several X-ray light sources that are around the world. And there are 4 other facilities like this that are funded by the Department of Energy. And what these are research facilities where people can come and they can study different phenomena from a lot of diverse communities, such as materials research, biology, geosciences, life sciences, security, and many more. And these light sources are emitting X-rays because the wavelength of an X-ray is about the same size as you would find an atom or a cell. So this type of research has really transformational positive outcomes for our society. So we're looking at creating the next solar panels that are going to be cheaper to manufacture and more energy efficient. We're looking to create batteries that have larger capacities and are easier to manufacture. We also want to map the human brain to understand ourselves and different neurological diseases. And we might be studying materials such as concrete to understand why do bridges fail. Or perhaps we want to look at rubber in your tires to make them last longer. And all of the many other materials that surround us in our lives. So this is coming at a really unique time, because currently the APS has just shut down for a complete upgrade. So they are going to replace the entire storage ring, and many of the beamlines are also going to get upgraded instruments, which are going to enable them to have even greater scientific research power. Similarly, the Aurora supercomputer is being built at another facility at Argonne, the Argonne Leadership Computing Facility. This is going to be an exascale machine, which we're going to be in a unique position to be able to partner with the ALCF to do our scientific research. So the upgraded Advanced Photon Source is going to provide us with a lot of opportunities, but it's also going to have with it a lot of data challenges, such as we're going to be seeing larger volumes of data, we're going to have much faster data rates, and we're also going to have to create new processing techniques. So to get an idea of the scale of this problem, we actually reached out to our beamline scientists, and we estimated, based on the new detectors that they were going to be getting and the techniques that they were going to be doing, how much data are they expecting to produce. And we found that we are going to be generating hundreds of petabytes of raw data per year. So this results in a 10-fold increase in the data that we are going to have to be able to process, which is going to require tens of petaflops of on-demand computing power. So the way that we are addressing these data challenges is that we've created the APS data management system, and this is also going to be taking advantage of a lot of these Globus services. So what the data management system provides is that it helps the beamline scientists with their data management tasks, such as having a storage area for their large quantities of data and being able to move the data from their local beamlines over to this storage area. We also want the users to be able to easily find their data and access it, which is why we provide a metadata catalog and remote access tools. We also want to be able to facilitate the processing and analysis by creating these automated real-time workflows or having them be initiated by the user. So of course, we are leveraging the many services provided by Globus. So we have Globus Connect Server 5 installed at our storage. And my colleague, John Hammonds, will be doing a deep dive tomorrow about how we upgraded to Globus Connect Server 5, so you can learn more about that. We're also going to be talking about an example specifically of how we're using the Globus flows and Globus compute to be able to accomplish these processing tasks. So, of course, we take advantage of Globus transfer. So this could be to transfer between the facilities that we have, or this might be a user that's come to do research can now use Globus transfer to transfer from our data storage back to their home institution. We're going to be using Globus groups to make sure that the data that we create in our science portals is only accessible by those users who should have access. And we're also using Globus Auth so that we can have flexible execution of these flows by service accounts, so that each individual user that comes to the facility doesn't need to have to set up their own Globus flows. They can instead run as these service accounts. So now I want to walk you through a specific example of one of the techniques that we are doing at the APS. So this technique is called X-ray photon correlation spectroscopy. And this is a technique that's done at beamline 8 IDI. So some of the research outcomes that come from this technique is it allows us to study parts of the human body, such as cartilage and joints, or viruses, or the effects of stress. We can also study materials such as plastics and batteries and glass and rubber, and also just normal things like toothpaste. So this amounts to hundreds of experiment users every year, which generates also hundreds of terabytes of data. We've created an automated workflow for this technique, and I'm going to walk you through it now. So the workflow starts here at the beamline where the data is collected. The X-rays are going to come from the Advanced Photon Source, and they're going to collide with the sample and bounce off of it. These photons are going to be collected by a detector, and that detector is going to write the data files to a local computer at the beamline. So this includes images and also metadata about the experiment that happened. Next, the APS data management has the TACC service, which monitors the local directory for these new files being written off of the detector. Then the DAC service will upload the file to our central APS storage. So this storage system is a GPFS file system, and it has 10 petabytes of data storage. And this is where all of the experiment data is going to be kept from all of the beamlines. So this is where we have our Globus Connect Server 5 endpoint installed, which means that after the experimenters come, they can go back home to their home institutions, and they can use their own Globus endpoints to be able to access their experiment data and process it further if they wish. Next, the data management processing service is going to start the XPCS workflow. So this is what the APS data management workflow engine definition of a workflow might look like. So you can see here we have a set of commands, and these commands are going to be executed in order. So what happens in that workflow is that first we're going to go and we're going to create a Globus group using the Globus API, and that is going to have the users from the experiment on it. And we know which users belong to the experiment because we also interface with the APS users database and the proposal database, which contains the list of users that were submitted as a part of the experiment proposal. Next, the XPCS workflow is going to start a Globus flow using Globus Compute, and then we're going to monitor the flow. So this is what our workflow looks like. So first, we want to transfer the files over to our HPC resources. Then we're going to acquire nodes on those machines. We're going to run the processing service to process our data. Then we are going to plot the results, gather the metadata, and publish it to a data portal. So we are able to use the Argonne Leadership Computing Facility, the supercomputer Polaris. And this is a 44 petaflop supercomputer. It has 560 different nodes. Each of these nodes has a 32-core CPU, and it has 4 NVIDIA A100 GPUs. So this is a very powerful machine, and because of these workflows, we're able to process our data in real time using these unique resources. And this partnership between a computing facility and a research facility is really unique because it's allowed us to do some things that are sort of special in terms of how both of the facilities are operating. For example, the ALCF has set aside specific queues for the APS workflows. So now, rather than having to have the users beforehand submit a request to have time at the computing facility, have them learn how to submit jobs to the queue, have to set up maybe their own FuncX compute endpoints over there, we've taken care of all of that so that they don't have to worry about their data processing. And these service accounts are allowing each of the beamlines to be able to submit their job as the service account rather than each user. So the user doesn't have to take care of these tasks. And the ALCF has made it so that rather than as some computing facilities might be optimizing the number of operations that they can get through, here we are instead optimizing the time to scientific results. So the XPCS Globus flow is then going to launch the processing package that is for this technique. So that is called the BoostCore High Performance Correlation Software. And this software is able to take advantage of the GPUs on Polaris and process the data to get the final results. So once the results have been created and we've created some plots of them and gathered the metadata, we're then going to publish the data to a data portal. And this data portal has been created using the Globus portal framework. So this is a part of the ALCF Community Data Co-op data portal. And so there are several groups that are also publishing their results here. So here you can see we also have some results such as groups who are doing tychography. There are people doing X-ray fluorescence spectroscopy, high energy diffraction microscopy, and also crystallography from the Institute of General Medicine and the Cancer Institute, which is the GMCA group. So once the results have been published to the data portal, the Globus group that we created earlier in the workflow is then applied to keep the data results secure. So only the users who are in that Globus group are then able to access the data in the data portal. So this is only one example of a lot of ongoing progress in automation that we have at the APS to build out workflows for different techniques. So we have 68 different beamlines who can all be running their own experiments at once. And here are some of the examples of other techniques, such as tomography, tychography, crystallography, Lowry microdiffraction, high energy diffraction microscopy, X-ray fluorescence spectroscopy, and fast X-ray Bragg peak analysis. So another unique progress that we've been able to have with this is that we were able to take data that was collected at SLAC, which is another facility over at Stanford, and we were able to bring it over to Argonne to be able to process it at our supercomputers. So we were able to take data at a facility that didn't have the compute resources, bring it over to ours, train an ML model, and then bring it back. And of course, this couldn't happen without collaboration between many different people. So I'd like to acknowledge the staff at the Argonne Leadership Computing Facility, the Data Science and Learning Group, the Globus Labs and Globus Professional Services teams, and also the APS, the Scientific Software and Data Management Group, all of the Beamline staff, and the, yeah, and also if you are interested in learning more about the Advanced Photon Source, learning about our upgrade project and all of the data challenges and solutions that we're creating, the APS director, Laurent Chapon, will be giving a talk tomorrow as well. Thank you very much. Any questions?
Our next speaker is another longtime friend of Globus. He is from the University of Saskatchewan, or USask, as the kids say, right? He's going to talk a little bit about using Globus Search to power their Lunaris dataset system. So Todd Tran is the senior software engineer at USask. So Todd, take it away.
How do I get to the next presentation?
You should be there. Okay.
I think I advanced to the end. No, I
thought it was.
no, I'm at the end of that one.
Okay. Could you? Okay, there we go.
Perfect.
And look, I did it myself 2 days time.
Good job, Greg. Thank you very much. Okay, so let's talk about data discovery, specifically finding research data sets that are open and are fair, as previously mentioned. So yeah, my name's Todd. I'm the tech lead for a team that works under the Digital Research Alliance of Canada, used to be called Compute Canada. We're working on two major projects. One is a research data repository, not the focus of today's talk, but we've been working on that since 2016. Next is research data discovery, today's talk. So this is what Lunaris looks like. And if I know a crowd of geeks, at least half of them are probably typing this into their browser now, and that's fine. You can do that and follow along while we do this. But a bit of history and how we got to where we are today and why we're doing this. And then we'll get into what we've done and how we're using Globus tools to make that happen. So in 2016, we did start building a research software data repository, sorry, a research data repository. And at the time, we were not the only one in Canada. We were just the newest. And the niche that we wanted to fill was what do we do for researchers that have large data sets? And at the time, the typical, like we have actually a data repository at University of Saskatchewan, but you kind of wouldn't know it because it's not heavily used. And if you go to our librarians and say, hey, I have a data set that's a terabyte, they'll go, yeah, there's nothing we can do. We don't have that amount of storage. Actually, that's more than we have on disk for our data set. Typically, what they've seen in the past before that was somebody coming up in 2016 with an Excel spreadsheet or two. So we built a data repository, and that's the Federated Research Data Repository, FRDR. You can see that in Canada now. And when we built it, we thought, well, okay, how are people going to find these data sets that the researchers put there? Now, well, maybe Google will just save us and we don't have to build anything. So we tried. We embedded JSON LD into the page source and then said, hey, Google, come search and crawl our site and find all our data sets. And then if you go into Google, and let's say that your data set is indexed and you want to find it later, well, good luck, because there's 3 million results and yours is not the top one. It's not even in the top first 1,000 pages, right? Unless you specifically know what you're looking for and you're the scientist that put it there, let's say, you're not going to find it. So we thought, well, we can help people find Canadian research data if we give them a place to search for it directly. So we did. 2017, thought, well, Globus, you've got a search engine that we can use. Let's take a look at using that. And the reason that we looked at Globus for this was A, we were already partnered with them for authentication and for data transfer. And B, they had Globus Search as a service. And all we have to do is learn how to use their APIs. We don't have to become the people that run Elasticsearch and deal with AWS and all the complexities behind load balancing, everything that the Globus Search team is good at doing. So we did that, and it's worked out wonderfully since then. So Lunaris is actually a rebrand and a rebuild of things that were already built. And I'll get into it now. So at the time that we launched our research data repository, there were others in Canada, like I said, and there still are. We're currently at least 100 repositories that we're indexing inside of Lunaris, but we started with 1, and then 2, and then 3 and 4, and we added more as we went. We started with the largest breadth one in Canada, which at the time was called Scholars Portal, and is now rebranded and is called Borealis. So that's a Dataverse repository. So we built something that would harvest that. And then we took a look at Open Data Canada, which is a CCAN repository. So we built something that would harvest that. And over time, we built this harvester that has, I don't know, at least 10 or 11 open protocols that it harvests from now. And what it was is a metadata harvester, right? Text only. So it would go out to all these different repositories, ask each repository, okay, what records do you have in your now? And have they changed? And he's deleted and he's, updated like that. But it was just metadata. So that's the first background. Second, we built on top of that, and the screenshots that I've seen in the presentations today about the default search portal that comes, I remember, yes, actually, our very first incantation of search was just that. So since then, we did deploy a discovery interface. That's the old one, not today. This is further discovery. And this was built on top of open discovery built at UBC, which they donated the code to us and we rebranded. So that was built on top of Globus Search at the time. Then we had a 2-year-long project funded by the Government of Canada through Canary that it was called Geodesy, that built a geographic harvester. So this is a little bit different. A metadata harvester goes to the repository and says, what records do you have? Give me all the metadata. The geographic harvester says, what records do you have? Great, I'm going to suck down the files. And I'm going to open up the files. I'm going to see if there's any geographic data inside any of those files and extract that. So it extracts points, bounding boxes, the actual geographic data. The only issue with that at the time was it was custom built for UBC because, again, the developers were out at University of British Columbia. And it was only on their UBC Circle, which was a Dataverse-backed repository. So they had a great and wonderful tool that could do more than just metadata harvesting, but just for one repository type. So I think you can put A and B together and see where we went with this. We took the existing further metadata harvester and we grafted in the parts that did the geographic harvesting. So all of our existing repository types now that we were currently we're harvesting through metadata only, we added on the geographic capabilities. So the Lunaris harvester is text plus geographic for every single repository type that we harvest. The output of this is gmeta, and it's just deposited into our Globus search index. The last piece of the puzzle, we went to Globus and said, we really want to keep using Globus search. It's been working out great for us for years. But what we want to be able to do is give a bounding box and say, within this bounding box, can you show us all of the results that fit inside that box? Because in addition to grabbing all the bounding boxes and storing them, we want people to be able to search by them and do a map-based search, as you're familiar to doing already with Google Maps, saying, okay, I want to see all the restaurants in this area. I'm downtown Chicago. Don't show me New York. Doesn't help me right now. So they did. We worked with the Globus search team to define the schema, and they did build this feature, and it's now inside of Globus search. And a big shout out to the Globus developers across the whole suite, because they publish docs at the same time they release code, which is crazy good. It's just, yeah. So if you take a look at the docs, they actually reflect what it does. There's a link in, of course you can't click that, but so the geospatial search user guide online is very good. So this is Lunaris. This is what we built. I'm not going to do a live demo. I'm going to invite you to try it out after the session. Reminder, we're currently in beta. We launched in beta March 29th of this year, so just brand new. And we're targeting our production release of May 17th. So right now, we're in beta phase. So if you, as willing participants in our beta search, would love to try out our search portal and actually break it, go ahead. If you find a search that doesn't work properly, then great, let us know. But what I've done here is I've given a search term. So I've started out with climate. And if you do that, you'll get, however many, 4,290 or so result, or 260 results just for the word climate. And at the moment that you do that, the map is turned off. So you enable the map and then you zoom into the area that you want. So what this is telling us is that 547 of our 4,260 results are climate data sets within this area of Canada, which is the western coast around Vancouver and Vancouver Island, around there. And if you take a look and you click on one of the results, then what you'll see is just the data set landing page like this. So it tells you all of the interesting metadata that, maybe this is a research data set that you'd like to reuse, and that's great. And what I'm not showing here because we're still building it. And what was still part of the original geographic harvester at the time with Geodesy was a geographic preview of the data. So because we have these bounding boxes, we can put them on the map and we can say, okay, for your specific data set, the data was collected here and here or wherever it is, or maybe some GeoTIFF files we can overlay on top of the map. So it will look nice, and that's coming up for production launch. But anyway, I was the Harvard presentation, beyond Globus Connect. I like that a lot because really using all parts of Globus, we're really interested. We're not using flows yet. I think we're actually going to get there fairly soon to automate some of our stuff. But using Globus Search more than just connect and auth is really important, and I think is going to be, as far as sharing and reusing research data in Canada, very, very useful. I was also a little bit humbled by some of the other presentations talking about the millions of data sets out there. Now we're comparing apples and oranges, but this is open data that is published in one of the repositories that we're harvesting. We still have more work to do in Canada in harvesting some of the other repositories that are not publishing, let's say, an open standard or something like that. And we probably have a lot more to do. We have had this signal coming from our funders in Canada that at some point in time, one of the requirements for getting funding for doing your research is that you'll deposit your data into a research repository someplace, either in Canada or maybe a domain-specific one, but someplace. So we built the infrastructure, so we have the repositories, we have the search, we're all ready for when it comes. If it comes, we'll be ready. The last part of this, and some of the things that Lunaris is allowing us to do inside of Canada, is we worked with the Canadian Association of Research Libraries, CARL, and some of the libraries across Canada have now implemented this Lunaris search as part of their catalog search. So if you're looking for something inside of specifically inside of the institution that you're at. So maybe University of Saskatchewan, somebody is looking for a search term, and it manages to hit one of our research data sets. As a result, then it's going to show up in their catalog search. We've also partnered with we've worked with Australian National Data Services, and we're starting to work with INRAE in France, and working together to try and find out how we as different countries globally can improve research search for data sets. So I'm the only thing standing between you and some supper, I think, but I'm happy to entertain some questions.
Hey Globus developers, my name is Louise, and I'm looking for your help to come up with ways to integrate Starfish with Globus. Starfish is a metadata and orchestration platform for research file systems. To demonstrate how simple it is, I'll show you how we can archive files in less than 30 seconds. So first, I'll select a directory, and then I'll add a tag called COVID-19. Then I will query for all files with the word medic somewhere in their path name, and that also have inherited this COVID-19 tag. I'll click search. As you can see, we have 104 results, and now I can perform an action, such as archiving. I select my desired target, and then I click confirm. It's that simple.